Hi, I'm Nils at nilsinside.com, and this is a part in the series of presentations explaining the energy converter by Carlberg. And I'm following up on Sophia's presentation that I recommend you to look at before continuing with this one. At Nils Inside, we develop a more efficient energy converter that will be the heart in many future external heat engines, and we believe that the energy converter has $1 billion market potential globally. This new engine is based on well-established thermodynamic and heat transfer theory. The news is that external heat engines has never been built in this way before. This is a completely new heat engine, unlike any of the existing technology on the market. The energy converter delivers unbeatable performance across a range of applications. Today's external heat engines are limited in power due to limited cylinder volumes. At Nils Inside, we have solved this by using a new revolutionary design, sweeping very large surface areas for heat transfer, breaking all old limits, thus allowing much larger cylinder volumes, that is, much more power. Because of this very good area to volume ratio, the energy converter can be built in a power range of a few kilowatts to several megawatts. The more heat energy it gets, the more compact and powerful it gets. On the other hand, the very good area to volume ratio also allows the energy converter to benefit from lower temperature differences than current heat engines. The lower the temperature difference, the larger the energy converter. Thanks to the ability to run on low-grade heat, energy converter applications will be able to recover $1 billion worth of waste heat in large scale that no other known technique are able to reach today. Joules found that heat and work are related. Both are forms of energy, and today they have the same quantity, joule, J. Energy is the ability to do work. A heat engine converts heat energy to work. The amount of energy does not increase or decrease during the transfer. It only changes from one form into another. In this case, heat energy to kinetic energy, and not all of the heat is changed into work. In a waste heat example, we will look at an energy converter configuration from a theoretical perspective, converting waste heat to electric power. Starting with questions, we will identify important parameters that we will relate to some proportionality statements. When this is done, we will be able to continue with formulas and finally set a chain of equations to calculate how much power we may convert from a certain waste, and put it all in a spreadsheet so we can present this in tables and diagrams. The waste heat example. The energy converter transfers heat energy to pressure pulses that we may use to produce work in one way or another. An electric motor controls the rotation of a working volume in a shutter between a warmer source and a cooler sink during the transfer. How to use the resulting alternating pressure to generate work is left open to an infinite number of possible applications. You may think of it in the same way as a steam boiler that generates a vapor pressure that may be used in different ways to generate work, that is, connecting a piston engine or a turbine or a pump, etc. A steam boiler gives you several options to generate work as kinetic energy. In this respect, the energy converter may be compared with a steam boiler. They are both parts of an energy system that provides several options to generate work. Important differences are that the energy converter delivers a ready-made alternating pressure instead of the old boiler one-way pressure. And the energy converter is not limited to steam. Is waste heat recovery a potential application? We will look at the waste heat with an almost infinite temperature of 90 degrees Celsius and a sink at 20 degrees Celsius, and we will use pistons to convert the alternating pressure pulses into kinetic energy to turn a generator. In thermodynamic terms, the energy converter acts as a closed system with a moving boundary that transforms an existing given temperature difference into a rotation by means of pistons on a shaft, and that this system in turn connects to an electric generator. But is it really possible to use a low-grade waste heat source to produce an important power output? Important questions. With an ideal gas as a fluid in a working volume, a low temperature difference always gives a corresponding low pressure, no matter how much volume we have. How are we going to get large quantities of energy from so-called low-grade heat? If more volume does not generate more pressure, why do we need a large working volume? But changing the temperature in large volumes is a time-consuming process. How are we going to heat up a large fluid working volume with heat from a solid magazine with a low difference in temperature between the magazine and the working volume? And how do we cool down the working volume fast enough when in contact with the sink? And also, choice of working fluid has an influence on power output. Is there a choice of gas working fluid that works in most applications? Is a phase shift in the working fluid a possibility? Under what circumstances do we gain power on a phase transition? With these questions, we have already identified important parameters. Temperature, uppercase T. The low-grade heat temperature difference between a source and a sink. Pressure, lowercase p. The low-grade heat results in a mild pressure pulse. Volume V. Our working volume will apply its pressure change to a solid area like a piston, a closed system with a moving boundary. Surface A. The low-grade heat is transferred from the source via a convector area into the working volume. The working volume fluid expands. Next step, the working volume fluid retracts while its heat is disposed via the convector surface area into the sink. Time, lowercase t. How many pulses we get over time will help us to calculate the power. We will tackle our waste heat recovery example in 3 steps. Step 1. Uppercase T, lowercase p, V, with the chapter Volume for Power. A closed system consisting of an ideal gas as a working volume and a moving boundary like a piston was fully elaborated, understood and documented by Carnot, Clapeyron and Clausius already in the mid-1800s. So today we have a solid theory and proven formulas explaining the interaction of the first 3 parameters: temperature T, pressure P and volume V, like the ideal gas law. P times V equals nRT. The product nR will remain constant in our first calculations, so we do not need to bother about them until later. Step 2. A, lowercase t, with chapter Surface for Heat Transfer. To understand how to heat up and cool down a large working volume as fast as possible is a question of surface area A and time, lowercase t. We will look at Newton's law of cooling to get an idea on how surface and time relates in heat transfer. Step 3. N, R, mentioned in step 1, are important in chapter Working Fluid and Volume. We have proportionality statements that will help us to understand how it all relates and how it works. These give an overview of the problem before looking into formulas and equations to get specific values. Statement. A temperature difference gives a pressure difference. In a sealed can with air, a temperature difference corresponds to a pressure difference. Statement. Pressure and volume creates work. A heat engine transforms pressure to work. And the relation pressure, lowercase p, times volume, V, tells how much work, W, you can get, lowercase p times V equals W. So, low pressure in a large volume may create the same amount of work as high pressure in a small volume. Statement. Power is how fast the work is done. Work per unit of time is power. When work is turning a wheel, the power relates to the rotation speed. Statement. Temperature and surface area sets the speed. Heat transfer is how fast you heat up and cool down the fluid in your sealed can. The temperature difference, how much surface area you have, and the velocity and distance of the fluid to the surface area sets the speed for heat transfer. The area to volume ratio is an indicator. Statement. Choice of working fluid sets power per unit volume. Temperature span and application decides choice of working fluid. High temperatures may benefit from a working fluid like helium, while operation with lower temperature differences may use a saturated vapor with a liquid vapor critical point suitable for the intended temperature range, letting a phase transition create a significantly higher pressure difference. Now you're introduced to the energy converter configured for a waste heat recovery in a theoretical perspective. Questions have revealed parameters to check with relevant proportionality statements. Now we are able to continue with formulas and equations to calculate how much power we may convert from a certain waste, and build a spreadsheet to present the profit in tables and diagrams. See you in next presentation, and thank you for watching. We need to raise $60,000 to start a planned project at the Department of Energy Science, Lund University, Sweden, to do a study on a lab module. Since mechanism of heat transfer and its optimization requires more scientific research and knowledge development. Results will be published in a research context in a first stage at a conference in the energy sector. Don't hesitate to contact if you want to take part in this. Take care. Bye.